that we're gonna shift this situation to this situations where at the end of the loading block reaches no tensile force. See, if you do this, the end of the compression loading block reaches zero tensions, so that your new foundations is gonna be on the compression side. Entire section is on the compression side. Your tension block of the foundation now ignored, removed, right here. So again, in this foundation, under overturning influence must be ignored, neglected. You can use this as foundation, as I said, so that your new foundations, enlarged foundations, with the zero at the left end of the compression block, will not cause any overturning moment situation. Do you understand? So now it's easy to follow. Let me just try to summarize one more time. When you have an overturning moment due to excessive eccentricity over there, we have to ignore the separated part of the foundations, and also we have enlarged foundations, ignoring the uplifted part of the foundations. Then we have a new foundation size over there. Now we have to adjust the foundation size so that the loading, upper loading, external loading, is passing through the centroid of the triangular compression loading block right there, so that entire foundation under considerations will not cause any overturning moment. So that we try to locate the loading in the kern or on the kern boundaries. This is the simple that we redesign the foundation when we have overturning moment. For if we have this situation, we're gonna resize the foundation so that the foundations will have a load on the boundary of kern, so that we can eliminate the overturning moment on the foundations. How do you do that? Making the outside of the foundation, the distance from the edge of the foundations and the loading, BR. And then you divide the rest of the dimensions into 2 alls, which means that your loading is going through a center of triangular compression loading, right? So this is all, then this should be 12, isn't it? In order for this loading is going passing through the center of the load block, as you see over there. So this is all, this is 12. Very easy, right? And this is center of the foundations. Then the all is calculated. See, this is L over 2, half of the foundation dimensions, right? Half over 2 minus E. Again, half over 2 minus E is equal to all. Very easy. This is very easy math. So here, if you see here, this is all. So all is nothing more than you subtract E from L over 2. This is L over 2. And this is E. So if you subtract E from L over 2, this is all right here. Okay. And from here to here, again, this is to all, right? Okay. So here we have the line of action of the external loading, vertical loading on the foundation is going through a centroid of the triangular bearing pressure block or triangular compression block. The line of action of P should go through the center of gravity of the compression block, right? Center of gravity of the compression block. This is all. This is all we need to do to get rid of this part of uplifted region from the foundations. Okay, everything is very clear by now, and this is new soil bearing pressure. This is new soil bearing pressure. New soil bearing pressure. Soil bearing pressure is the loading, external loading. It's like our enemy. We have to get prepared against this external loading, our enemy. And this Pmax, which is new soil bearing pressure under new foundations. Okay, new soil bearing pressure under new foundations. Then this Pmax, how we calculate this Pmax? Pmax is calculated based on the volume of this soil bearing pressure. This is new soil bearing pressure. I could say new compression force under new foundations. Okay, right. So this volume is 3R times, okay, let me change the color, 3R times S times the new soil bearing max right there, and then divided by 2 right there. This is triangle, right? This is 3R S Pmax divided by 2. So that Pmax is calculated, you know P, you know S, the width of the foundations, and you know all, right? So you know everything, so you can calculate. This is known. This is known, right? This is known. So you can calculate this. Very easy. All is, let me just say it again, all is L over 2 minus E. So we know the eccentricity, we know the length of the foundations. Right? So understanding all in terms of eccentricity, we use that later to come up with the Pmax over there. All right, so now we calculate the volume of this compression block. Okay, so what's the volume? This times this. This is 3R, and this is the width of the foundation, which is S, times the soil pressure, which is Pmax, and divided by 2, which represent total compression force for this compression block. Okay? So we easily calculate the soil pressure acting on the corner of the foundations are probably 2P divided by 3 all S. Okay, 3 all S. And then we go compare these values, this value to which allowable soil bearing pressure. Allowable soil bearing pressure. So when allowable soil bearing pressure is greater than Pmax, then we're okay, otherwise not okay. We have to do something else. Now we'll take a look at some example of shallow foundation design. We have 3 types, as I said. The first type is where the stress from vertical stress overcomes the stress from lateral stress. That's case number 1. Okay, this. And the second type is the opposite case where the stress from overturning moment is greater than the stress from vertical load, which allows us to have a tensile zones. Okay, and we're going to take a look at these 2 cases and one in the middle, so how we can design the foundation and see how the foundation size varies depending on these loading conditions. The first case is where we have a loadings here, okay, and the size of foundation must be determined first. How we determine the size of the foundation first, that's easy. We know that we have a foundation thickness and we know the density of soils. So from here, we can calculate the loading on the foundation, which must be subtracted from allowable bearing capacity of soils. And also we have surcharges as well. So net soil bearing capacity is simply calculate bearing capacity, allowable bearing capacity. This is allowable bearing capacity. Allowable bearing capacity minus concrete loadings, surcharge load. This is concrete loading. This is concrete loading. This is surcharge. We have to subtract these 2 loadings from net bearing capacity. We end up this number. So this is net bearing capacity. And we divide total actual loads by this net bearing capacity. We end up as some area which is required to support under these loading conditions. Okay, and this is the initial size of foundations. The first case where we don't have a too much eccentricity, where we have a bigger stress due to vertical load than the stress due to the overturnings. This is small eccentricity. For example, the eccentricity in terms of the length is 0.4 feet. Okay, so now we calculate to see if we have a tensions underneath the foundation or not. We calculate this value and this value. Okay, this value is this calculate from mi over I. Okay, mi over I. And this A, we know the A, and we calculated area, this, we will assume 5 feet, 9 feet, 5 feet by 9 feet foundation gives you 40, 45 feet, it's greater than 33. So we just start with these foundations here, and we calculate this value. Okay, let's calculate the stress due to the moments. This is again my over I equal m m divided by I over y equal, well, I cannot write well. And m is force, vertical load, P, and eccentricity. Gives you moment. I can write. And I over y is C. Okay, C. So C is what? C is the HO2. So, and this is all given. I equal y. BH cube divided by 12. What's wrong with the pen? Yeah. Now let's take a look at it here. How you calculate I. And this is foundations. Okay. This is foundations, and your moment is acting this way. Right? When moment acting this way, then how you calculate your moment of inertia. And the axis parallel to the axis of moment is B in structural mechanics, right? So the moment axis right there, which is parallel to B. So this is B, size B equal 5, right? It's given, it's 5. And the axis, which is perpendicular to the axis of moment, as h, height, right? So height is 9, as given. So I value is this 5, 9 cube over 12, and C is half of h, which is 9 over 2. Okay, so you plug all these values into here, and P is for 400,000, and eccentricity is given here 0.4 feet, and you plug all these values, put them here over there, you calculate two values, plus and minus. So one goes plus, one goes minus, right? So you have a 1100, 11,000, 6,500. All this is compression because you have a smaller overturning moment, right? In this particular example, you have to be very careful in calculating correct I based on correct understanding of the dimensions, which is B, which is H. Okay, when you're not sure about it, you take a look at the axis of moment, whether it is a parallel or it is perpendicular. If it is parallel, then that's B. If it is perpendicular, that's H. Okay, now we have the critical stress, right here on your foundation, and compare that to the allowable bearing stress. So allowable bearing stress is where? From this, right here, 12040. So this is a 12010 is missing here, right? 120. Well, I don't know how to write it. I can't write it. 12040. So the net bearing pressure is greater than the stress acting from the loadings. So your foundation is okay. It is 5 by 9 feet when eccentricity is 0.4 foot. Next example is one similar to one we saw, where we have a eccentricity of 1.3 feet. Okay, and the calculation process are identical. We calculate stress due to vertical load. We calculate stress due to moments. And here, knowing that the eccentricity increases a little bit, so we just assume that we increase foundation a little bit to 6 by 10. Okay, it's a trial error. It's just end up with any foundation you could think of as stutters. So this is a vertical induced stresses. This is a overturning induced stresses where the I and C value are calculated identically as before. Now here you have plus minus two cases depending on the direction of the moment. In either case is yielded the positive value, right? Whether this is plus or this is not a positive value, which means that you're not having a overturning situation where you have a tension underneath the foundations. So you can still apply same formula to check if your stress is okay or not. I mean, bearing capacity is okay or not. So your bearing capacity is still okay. And this is your stress is caused by the loading both from vertical and horizontal, which is less than your allowable bearing capacity, which is 12,000. We're still okay. Think if you didn't change it, the size of foundation, it not be okay. Not been okay. So it depends on engineers' trial error technique in a sense that we can save number of efforts to come up with a appropriate size of the foundations when loading and eccentricity changes. Change of eccentricity means change of overturning moment. That's same terms, right? Now the third case, last case, is also very important where we have a very big eccentricities, which is 2.2 feet. That means that we have very big overturning moment. And we want to see if we have to do something else other than things that we've done for previous examples. Okay, now let's calculate. And before we calculate, we also assume that the foundation has been increased to 711. How? This is again based on your hunch, your guess, right? So this is a vertical stress. This is a stress from vertical, stress from overturning moment, which is from eccentricity. I calculate this, and this is easy again. You keep it careful. Was B and was H. So in this case, B is 7, H is 11, right? You take a look at a axis of moment and compare with the direction of the dimension, which is B and H. You can simply determine which is which. Now calculate here and assess the value depending on these two signs over there, depending on the direction of the turning moment. And you have a certainly minus case, right? Even if you increase the size of the foundation, you have minus, which means that you have a tensile stress underneath your foundation, which means that your foundation needs to be something done. Because there's some portion that you cannot use as a foundation on this particular loading combinations. Okay? So the thing is, how we're gonna do? We have to check everything's okay, especially the bearing pressure at this particular region. Bearing pressure at this particular edge of the foundation is okay or not. So what do you have to do to check if your bearing capacity is okay or not is to calculate stress. Stress right here caused by the external loading and compare them to allowable bearing capacity, of course, right? So how do you calculate the stress underneath this particular point where you have a tension underneath the foundations, we have looked at it, how to calculate this formula, right? We calculate the area of this block, and we calculate it. We subtract it. We extract P max from that volume of force. Okay, and all this we have divided into three, right? And this is eccentricity. Eccentricity is located at half of the section. This is half of the section, right? So the all is nothing more than a L over 2 minus E. L over 2 minus E. So this is a all. So we plug all numbers as far as we know that. We know P, actual load. We know S. S is this dimension, isn't it? We increase to 7. And L is 11. We increase to 11. And this is eccentricity and whatever. So that this is the actual bearing pressure. This is not a allowable pressure. This is allowable pressure. Allowable pressure don't change it, but bearing pressure changes all the time, depending on the size of the foundations and eccentricities and external loading. Right? This bearing stress changing all the times, but your allowable net bearing pressure don't change. It's the same as long as you don't do anything for soils to strengthen them, right? So this is okay right now when you consider, even if you consider the tensile region underneath the foundations. Okay? And this is how you check your foundation and design your foundation when you have an extreme overturning moment. This case is very important, especially when you have a foundations for cranes. Cranes is the structure that transmit very high overturning moment to the foundations, where the foundation experience severe overturning leading to severe tensions at certain region of the foundation underneath. And where you have to calculate the capacity considering only compression block like this, and compare that to the bearing capacity like this, and check if you need, if this does not hold, it means that this value, your pressure from loading is greater than bearing capacity, allowed bearing capacity, then you have to go and increase your foundation size more right here to maybe 8 to 12. It depends on trial error technique, which is easiest. You can calculate, you can repeat the same calculation until this value is smaller than this value, or this value, which is allowable bearing capacity, is greater than the stress that caused by this. Thank you very much. We're going to stop here for the week 1 lectures. Please take a look at this video clip carefully, and we're going back. We're coming back with more examples next time.